So, tools of chemistry, right? I think they should call this cheap tools of chemistry because that's what we have up here. But really, almost pretty much everything on this tabletop, with a few maybe some funnels and things, you can do everything that they did in Breaking Bad. So there's a lot of stuff you can do with the cheap tools of chemistry. When I think of tools of chemistry, I'm more thinking of high-performance liquid chromatography, solid phase microextract, just all the fancy electronic tools and buttons, right? But you got to start somewhere, and so much can get done here on just $20. So, but we need to talk about the general tools of chemistry and sig figs, significant figures. And if you don't do this stuff right, I mean, the errors can be huge, right? 63% of wrongful convictions are featured because of people screwed up in the forensic science lab. So it could be sig figs, it could be calculations, it could be just bad technique. So you got to be careful. So before you do anything, though, I guess safety is numero uno, right? So let's see. Yeah, wear those goggles. Okay. Why should contact lenses? Where are all my quizzes? Andrew, let's say you wear contact lenses. Do you wear contact lenses? Oh, you do wear contact lenses. Okay. Andrew wears contact lenses. Let's put the question this way. Andrew wears contact lenses. He goes in the lab. What needs to be there for him to be in trouble with those contact lenses? A gas. A gas that's permeable to those contact lenses, right? So a gas that, when mixes with water in your eyeball, gets really acidic, right? And then you're in trouble. Pretty much every acid you use is really a gaseous acid dissolved in water. So that means they're all fuming. So, and you don't know it unless you use the concentrated 12.1 molar nitric acid, for example. Then you can actually see the fumes, right? So that's the danger. That's why you can't wear contact lenses in lab, because imagine it burns. Oh, you can wash it out all day, right? You got the stupid contact lens. It's between the contact lens and your eyeballs where the damage is going on. So that would be ugly, right? So that's never happened. I'm surprised it hasn't happened in lab, but hope it never does.
I was working with the 12.1 molar HCl yesterday, but we were doing it under the hood. So
yeah, see the hood, but let's say, you kind of screw up, right? You kind of waft the 12.1 molar out of the hood and back in. Yeah, then you're exposed to it. But you're right. If you do things in the hood, hell, if you do things in the hood, if you did them right, you don't even need safety glasses because you bring the shield down, right? So the hood is awesome. And a chemical hazards label. So these things are on the bottles. And I went and I grabbed one. And then I brought it back here. Then I thought, let's see. I grabbed it from the refrigerator. So it's cold, right? What happens to something that's extremely flammable as it warms up? It's going to expand, right? It really wants to volatilize. So I'm going to build up a lot of pressure in here. Probably set it over here by Jesus and Zach, right? Down there. And I'll stay over here. I was thinking, I'll just put it back in the fridge. So I put it back in the fridge. Anyway, these numbers go from what to what in this chemical hazards label? That's what I thought. The book says 0 through 3. So I thought the top number was 3, but that label had a 4 on it. So I think it goes from 0 to 4. Now, what does each color represent? Let's say...
I'm sorry, so is 0 to 4 the right answer?
I say 0 to 4.
Okay.
Because that's what that dang label said. You've got a 4... I can't see it very well there. Caroline, you've got a 4 in the blue box. How should that chemical be handled? What should you do special about it? All right? What do you think? I'll give you a hint. Something with a 4 in it should not even be in an undergraduate chemistry laboratory. Something with a 4 on it, I would have the goggles, I would have the gloves, I'd have the aprons. This stuff wouldn't even be opened unless it was in the fume hood. What kind of compound is this? Something that's really what? That's what? Man, I'm really worried about it touching my skin. It's really toxic, corrosive, something that's really unhealthy, right? That's the health box. So you have a 4 in there. It shouldn't even really be in your undergraduate laboratory. Okay.
So 0 to 4 is severity, and blue is the health box.
That's right.
What a
You
different
have
person.
blue is a health box. Health. You have a 4 in the red box. Zach, how would you handle that compound differently than other compounds?
That one would be highly flammable.
So how would you handle it differently? You're right.
Keep it nowhere near a Bunsen burner.
Yeah. It shouldn't even be in that room. Yeah.
Don't do anything volatile.
Yeah.
It has to be somewhere.
Yeah.
Not violent.
And it should be stored with other compounds that are highly flammable, right? They're all stored in that metal arrestor box,
Yep.
right? Okay. You have a compound that has a 4 in the yellow box. Mariella, what's so special about that compound then? How would you treat it differently? What's that? How would you handle it differently? I'll give you a hint. I don't know. Let's say here's a cap. This is a bottle. I can't really seal it, but you have to pretend this is a bottle, okay? And it's been sitting in the chemical storage area over there behind Mungia's office, and there's dust on it and everything. And you look at it, and then it's probably not even yellow anymore, right? But it's got a 4 in that box in the corner. This is what I would be doing. Oh my God. I carry it without shaking it at all and get it the hell out of there, and then maybe not even carry it. I'd have a metal container or something right to put it in, seal it up, and oh my God, okay, now let's get rid of it. It's explosive in the sense, explosive isn't the right word though. It's unstable. It decomposes. So what makes this thing so dangerous then? If it decomposes, it's building up a what inside there? Pressure. It's building up a lot of pressure. It's decomposing. You don't really care what's decomposing to. It's unstable. So whatever it was, it's decomposing into more than what it was. It's going to build up a lot of pressure. So peroxides are especially bad with that. How about the white box? Anybody know what that one is? I've never really seen anything in a white box, but it's just special conditions. Yeah, I don't know. Don't store me next to blah. Okay. I'm reactive with air. Keep me in the refrigerator. Right? Whatever the manufacturer wants to put there. Okay. Why would technique be important in a forensic science lab? Well, we kind of already know that, right? So, a research lab, again, you don't want to screw up and then it's going to take forever to catch your error, right? So, yeah, a good technique is important. So that's kind of what I want to illustrate over here. I don't know if it's good technique. What I know is that this gives me really good results. Because no one's ever said what good technique is for, at least for me, for massing something. So, but you're going to have to do this in the lab a lot. So what good technique to me is something that gives you very highly precise results. Right? You get the same measurement over and over again. So if I want to mass, I need to mass something, right, and get the mass of it. So the first thing I do is fold the paper. It's so much easier to get in and out of there then, right, and to get it out. So, and then I don't like to do math. So, wow, he's touching the edges. Did you see that? Touching the edges of the balance. Okay. This will be a lot better. Then I don't like to do math, so I'm going to tear it. What does tearing do? Zeros it. Right. Okay. You notice when I pushed it, the whole balance moved? So it's not set up right, right? Whenever you're going to look at the balance, look in the back, and there's always a little level, and the little bubble should be in the center. Right? So I didn't take the time to do it, so you didn't see it happen. Okay, so it's zeroed. Then, and notice all the windows are closed. Get my little micro spatula. Okay. Open up the side. And I open up the side so that's right in line with where I want to work. Right? So then I can do the little tapping thing. And the tapping thing is nice because then I can get whatever mass I want. A lot of times, oh, get 0.01 grams or whatever the case is, right? So I was going to dump it all on there so you have something to see. 0.09, whoop, close it. What does that say, Destiny?
0.0924.
Okay. And if you wanted, really, to prep us for what's coming up in the future, you may not take P-chem, but this is always subjective. What's your error in that measurement? Well, a lot of times if he's bouncing around the last digit. He's not even bouncing around. But I guess you got to give him some kind of error. This is where it's subjective. Do I put a 1 here? Or do I, right, because that would follow with this digit. But he's not bouncing around. So I could go even further and say, put a 0 in there and say a 5 or something. That's kind of subjective, this whole error thing is. Okay. This is tradition. Tradition is 0.0002. I don't know why. It's not bouncing around. We paid a lot of money for that balance. Right? He's not bouncing around, going from 2 to 6. Anyway, but I guess if the best way to figure this out, does anybody know? Do what? Standard deviation. Take it out, put it on, take it out, put it on, right? Do that like 10, 20 times. Find the standard deviation. And I guess it comes out hopefully to something like that maybe. I don't know. That could just be fingerprints. Okay, there's how we get our mass. How is an analytical balance calibrated? Well, usually you can just push the calibrate button. And then you hear this, right? And there's nothing stopping you from doing that, right? You push the calibrate button and that calibrates it. You can also, if you have an El Cheapo balance like this one, you have to push it in calibration mode and then put on a known mass that it expects. And this is exactly 100 grams. So you put that on there and let it equilibrate and it'll be calibrated. I guess one bad thing would be, because I said that you could go ahead and push the calibrate button. I wouldn't. Because let's say Naya comes up here to measure something. Then Mateo comes up here, but Naya pushed the calibrate button. Mateo used it before to measure it. Now it's got a different 0. Everything's off. So really, honestly, you don't care about calibration because you just have to use the same balance every single time. Everything in the lab is about changes. How did this mass change? So if you tear it, put something on, you just found a difference between your 0 and what you have. So that's a difference. So if it's not calibrated, you really don't care. Okay. So, but the key to making this work is to use the same balance. If we want students to jump from one balance to the other, we better have all these calibrated and extremely well. But I don't. So use the same balance. They're all calibrated, and I think you could get by. Big long line on balance number 9. Ah, shoot. I'll go use balance number 8. You should be okay. But I'm just saying you should use the same balance every time. Okay. Buoyancy. Okay, what is buoyancy? I got to save this for later. In fact, I might as well just put it in my flask. I'm going to put it in here right away because we're going to need it for later. Okay, now there's probably still some little salt on there, so I'm just going to set it off to the side here. We'll mess with it later. Buoyancy. I'm working on a revised way to teach general chemistry lab, and one of those activities involves, where's my syringe? Oh, here it is. one of those activities involves taking a Bic lighter, release it, let go. What's the new mass of the lighter? And you got to predict it. Okay? And in developing that lab, I learned about buoyancy on my own. I've always heard about buoyancy, but what the hell is it? With balances, buoyancy, buoyancy, buoyancy. You have buoyancy air. Okay. What I want to do is I want to find the mass of this syringe empty. Okay? I can find the mass of the syringe like this, or I could find the mass of the syringe. Okay, I'll just see if I can get this. See, there's a what do you call it, rubber stopper there. So when I pull it, I'm just pulling a vacuum. Right? So I'm not pulling air in there, right? So whether I find the mass of the empty syringe like this, or I find the mass of an empty syringe. Let's see. There's a hole. Let's see. Like this. Shouldn't matter, right? One way is wrong, one way is right. One way, in fact, is very wrong. One way, in fact, is very right. Okay, so let me show you what I'm talking about. Because let's write down the okay. Let's write down the mass. Oh, I need this nail in there. Oh, Brad, write down this mass on the chalkboard there or something. Put it on there. Oh, yeah, I got to get this on there. Oh, I can't close it. Well, let's just make sure let's make sure he's teared. We'll just have to leave the top open. We're just kind of stuck.
Don't blow on it. Nobody blow on it.
Yeah, everybody stop. Stop breathing. Okay, 80.1564. 80.1564. Yep. Okay. Now I'm going to pop it open. I can go all the way to this guy. Ah, shoot. Can you hold that for me? Thanks.
Do a show.
I can do it. I can do Dr. Smith.
I don't know. I'm getting so old. I gotta start lifting weights or something.
CrossFit.
Ah.
I'm telling you, CrossFit.
Okay.
So sore.
Okay, you ready? 79.9890. 79.9890. Okay. What's the issue here? The issue here is it's kind of hard for you to go from the gas lighter to this, but the point is you had, in this activity, you have to measure a volume of gas. So you fill this guy up, stick it in a bag. Wow, make life a lot easier. So you want to fill this up with oxygen and mass it or something, right? So you stick in a Ziploc bag of oxygen, fill it, suck it up, right? So it's full of oxygen, cap it, right? And you could find the mass of this whole setup. But you have to find the mass of this guy empty in order to find the mass of the gas, right? Because you have to subtract this one minus the mass of it empty. The question is, what's the true mass of it empty? Does it have to be oriented like this, or does it have to be oriented like this? Because they are two totally different numbers, right? Which one is the true zero? Is the true zero this one? Or is the true zero the one where, Shelby, help me out? The answer is buoyancy. The true zero is this one, right, where it's set up. Because it needs to have the exact same density it had before. The volume really changed on you. There's a huge difference in volume between what you're measuring here and between what you're measuring here. Big difference in volume. We don't think of ourselves as floating in air, but we are. We just suck at floating. We're at the bottom. But still, you are buoyant. You don't feel it, but you are buoyant, right? So, yeah, like I said, we're not very, very buoyant, but there is a degree of buoyancy to you. So if you want to measure the mass of something, buoyancy can really mess you over. But if you're measuring a solid and he has this volume pretty much all the time, there's no buoyancy error. It's the same thing pretty much. So buoyancy really has to do with the density of what you're measuring, right? It can't change on you. So that you only see that effect when you start trying to measure the volume, start trying to measure the mass of a volume of gas. That's what buoyancy is. Don't mess with density. Volumetric glassware. Which one do you not want to store in, here it is, in here? What would you say? Alyssa, what would you say? .33% chance. One of these compounds eats up glass. Eat up glass. So, I mean, to a very small degree, but in an anal laboratory, you're anal, so it matters, right? What is the tolerance of a 100 ml volumetric flask? Well, Eric, what does that say? Plus or minus?
Plus or minus 0.16 milliliters.
Yeah, so it depends on, we can write that here, but it depends on how much money you're going to spend on that flask. There's good ones and there's bad ones, right? That's what this one is, made by Pyrex. Okay.
What does that mean, though?
So it's the error. Good question. The tolerance is the error. It's kind of like with that, when we wrote the mass of this number. We're trying to say that whatever number you wrote, this number really is 0.0922, somewhere between there and 0.0926. You really don't know where it is. It's somewhere in between those two with a 90-some% probability. We'll get into confidence intervals later, but that's what it means. So same with this volumetric flask. If you filled it up, you're saying you have 100 milliliters plus or minus 0.16 milliliters.
It's the tolerance refers to the accuracy.
Yeah. Yep. How close you are to the right answer. The range.
Is that accuracy or precision? Precision.
I would say this is talking about accuracy because it's talking about how close you are to the right answer. Precision is, well, it also refers to precision. Because if you do this many times, you should be having 100 mils plus or minus 0.16 milliliters. You should be falling in that range. So you really can't have one without the other with accuracy and precision. If you had it's a good question. If you had a target at an FBI range, I remember me doing this in Gen Chem. That's supposed to be a guy. And you're going to... Yeah, it is Patrick. Okay, you got to kill Patrick. You got to shoot him in the head or the heart. So you line up right there. That's his head. So someone nailed him in the forehead. You can't say that is accurate because he only did it once. The guy could have closed his eyes and right. So you can't have accuracy without precision. That's just.
So precision is
the repeatability. But the key is of doing the same thing over and over and over again. It can't be different things. It has to be the exact same thing you're doing over and over again.
So repeated accuracy.
All right.
Precision.
Well, something's only accurate if you do it. If you can do it again. Otherwise, I could just close my eyes and nail Kevin in the head.
But that's just precision, isn't it?
No, precision. I have to do it again and again and again. But if I just do it once, I could have been closing my eyes and saying, "May the force be with me." That's right.
Because then the accuracy is
So it's kind of a.
that you're right on the spot.
I'm just trying to say what the statisticians say. It sounds pretty accurate to me. I hit what I was aiming for, but they say no. You have to be able to have some degree of precision with it to talk about accuracy.
Accuracy has to
Precision is just the degree of how well you can repeat something. Accuracy is how close you are to the true result. But just doing it once doesn't count for accuracy. You have to do it several times, is what they're saying. That's just what some statisticians say. So it's kind of odd. Can a 100 mil volumetric flask be used to deliver 100 mils with this same tolerance? Oh, Jose, go get me 100 mils. So he runs and he grabs this thing, fills it up, and he says, okay, here you go, and dumps it into the beaker. Is what he dumped into the beaker 100 mils plus or minus 0.16 mils? No, it's 100 mils plus or minus 0.16 mils if he uses this container. It's not meant to deliver anything. You have to keep it in here. That's the 100 mils. If you try pouring it out, I mean, you're going to see stuff on the sides, and it's going to leave. No way, man. No, you can't use this to get 100 mils plus or minus 0.16 mils. Oh, that won't work. It's used to make solutions, not to dispense them. Okay, so the answer is no. Using the mass sodium chloride, oh, here it is, and the 100 mil flask, what will the concentration of sodium chloride equal? How would you make this solution? Okay, Shelby. Well, I already dumped it in there. How would you make this solution? All right? I dumped the sodium chloride in there. All right? And this is my water. Just so you can see it. All you got to do is pretty much just what? I had a little, here he is. Keep going. Go ahead. Yeah, what are you supposed to do? That's what I'm asking you. Do I have a funnel? I don't have a funnel, so let's do it. Let me do it over the sink. I thought I had everything I needed. There's too much stuff to bring today. All right. But you go ahead, while I do this, go ahead and calculate the concentration of the sodium chloride in here. You didn't write it in your notes? Hopefully somebody did. .0924 I hear is the mass of the sodium chloride. Look at that. Ooh, I got so lucky. Okay. Right? Someone did the study. Sodium chloride was in there. Let's assume it's all dissolved at the bottom. Just pretend it is. It's not yet. But pretend it was. Dissolved really easy. Pretend. How many times do you have to invert this to actually mix the solution? Someone did the study. It's 12. You have to physically do this 12 times. If it's dissolved, if it's all dissolved. If it's not all dissolved, well then, once it all dissolves, then it's 12 times.
Does it matter the concentration? Like if you have super saturated solution.
Oh, I'm just talking about a homogeneous solution that, you know, a typical normal solution, no tricks. Just to get a solution well mixed after you prepare it, 12 inversions. I remember doing a lab, and this guy was doing these titrations. He had results all over the place. He just didn't do this. He just didn't mix it really well. And so that really bit the big one. You have to start all over. Yeah, and use your thumb. That's why it's all blue now. Okay. So what'd you get as an answer for the concentration of sodium chloride? Did anybody get it? 0.924 molar. So you took the grams, divided by the molar mass. Ah! I hear 0.0158 molar. No, that's grams per liter. That's not moles per liter.
Oh, yeah.
We had 0.0924 grams.
23 plus 35, so 48, roughly 48 grams per mole.
Right?
58.45 is the molar mass.
Oh, 58.45 is the molar mass. Right? Okay. Is the final answer?
Yeah, 0.015.
So somewhere around there, 0.016 or somewhere around there.
And scale it up. So you calculate for a whole liter, and we're using 100 mils, which is a tenth of a liter. So you need to multiply your answer by 10.
It's 0.1 liters.
So moles over 0.1 liters. Right? Okay, so something like that, right? And you saw how we mix it and how we prepared it. How about the pipette? You remember how to use these things? They are probably the least fun thing that you've used. Right? Remember, first you get the air out of the top. Remember doing this? I should have you guys demonstrate this instead of laughing at me. But the only trick I have to doing this is I have my thumb right up here, because that's the trick that I have. I go way past the line, and then I pop it off with my thumb, and it's so much easier to control. Bring it up to your eye so you avoid the P word. What's the P word? Parallax. Now I'm ready to dispense. Right? Okay. The meniscus. You've seen the burette, right? You fill it up and you have this little bubble. You read the bottom of the bubble. Make sure you read straight across from it so you avoid parallax. What is meant by bringing a solid to constant mass? You just keep heating it, keep heating it, keep heating it, or let it cool, mass it. Put it in the oven, heat it, cool it, mass it. Heat it, cool it, mass it. Heat it, cool it, mass it. You're just trying to drive off all the water, right? That's what bringing to constant mass is. Any advantage of using a microwave oven? Well, it's faster. Okay.
What was the tolerance of that pipette? The top thing? Okay.
Oh, what's the tolerance of a pipette? You just have to read on there. I don't know, good question. See if Alyssa can see it. Oh, man. You have to find a pipette that has one on it. But they're all going to say plus or minus something. This one doesn't have anything on it. Usually it's like 0.01 milliliters or something like that. But you just have to find it on the pipette itself. Experimental error. When you're reading these and you want to write down plus or minus, again, it's subjective. But generally the rule is this is the general rule, plus or minus 1/2 the smallest division. So the typical burette has to the tenths place, so you'd write plus or minus 0.05 if you wanted to, or just write plus or minus 0.1. If you want to read it from way back here, write plus or minus 1 milliliter. It's very subjective how you determine tolerance, right? With a meter stick, graduated cylinder, it's always just plus or minus 1/2 the smallest division. Significant figures. This is it. Okay. Let's take a look at this hardest one right down here. How many sig figs are in that measurement? Just guess. Okay. There's an easy way to do this. What you do is, see, they're kind of answered all over the place. Write it in scientific notation. And then all these zeros that aren't important, that are insignificant, just disappear. And you write in scientific notation, you get a number between 1 and 10. And everything that's left, you write down. So I'm going to get this between 1 and 10, the decimal place. I got to be moving it to the right. I end up moving it 3 times. These 3 zeros disappeared. Nothing else did. So I move it 3 times, write down everything that's left. So 1.5020 times 10 to the positive 3 or negative 3? Negative, because it's a small number. Number of sig figs, just count everything. 1, 2, 3, 4, 5. So if you said 5, which a lot of people did, you're right. So that's how you do all these. Write it in scientific notation, and then you just count the digits. How about this last one? if you write in scientific notation, it's going to end up being 1. There's no 0 here. So you're going to move the decimal point over here and write down write down what you have. You have 1 point. I mean, you don't even really have to write the 1 point. I mean, you don't have to really write the point. A lot of people don't. It's just 1. There's no 0 after it. This isn't there. That's not there. So it's just 1 times 10 to the negative 2/4. 2/4. Isn't? Yeah, you're right. 6. I can't even count. 1. Okay. So that's the game with sig figs, and you can practice them if you'd like. Okay. 4 moves.
4 rules, like in physics, you presented it to us, like 4 rules where it's like.
No, there's no rules. You write everything in scientific notation, and then you count digits. No rules. We'll have rules coming up later for you, Eric. That'll make you happy. Man, we're out of time. Yeah, so much fun. Time goes so fast when you're having fun. Uh-huh.